Welcome back everyone. So today we are going to learn about configurations. How we can define various configurations to build a good map and how it can work in order to make the maps better. So what we need to make a map are these two things, a laser data and an odometry data. If we can generate these two properly and give relationships related to them in proper manner, we can have a perfect map, and that can be done inside the SLAM-G mapping node. So let's first see what are these datas, laser data and odometry data. So we'll first see all the topics right now, and we'll see that there are two topics, Kobuki laser scan and ODOM in our case, which is generating these datas. So let's first echo the Kobuki laser scan topic and see if anything is there. So yeah, it's working, and let's confirm it with ODOM also. So yes, we have both of these things ready with us. Now we have to understand what are these two topics. These two topics are generated by two devices here. One of the device is this one and one of the device is this one. So the laser scan is generated by this small scanner, which is a separate device, and the odom is generated by this base, which is like the robot, and there are some sensors inside the wheel of this robot which is generating the odom. Since these are two different devices and two different datas which are generated by those devices, we have to tell the relationship between those two devices in order to generate a relationship between those two datas. To speak in very easy language, we have to define whether the robot is looking forward and the other device is also looking forward, or is it looking backward. We have to define whether the robot has its base at a very bottom or it is at some height, its center of mass is at some height, whether we have the laser at a height of 2 meters or 20 meters. We have to define that relationship also with respect to the robot's base. If we have all this information correctly, only then we can generate a similar kind of a robot working in our simulation and in the software. We have to take it as close to as real world as possible, and this can be done by defining something called transforms. So the transforms are nothing but the relationship between frames, two frames, and one of the frame here that we are using is the base link frame, and the other frame that we are using is laser link frame. We can view all the frames by running this command ROS run tf view frames, and this will generate a frames.pdf. We already have one here, but I still generated you one. So let's first download it and let's see what is inside it. So this is a very big file because many frames are involved, but the frame that we are interested in right now are the laser link frame and the base link frame. So laser link, I mean laser sensor link is here and the base link is here. So since these two are connected, we know that there is a relationship existing between these two. So we call the laser sensor link a child of base link, which is its parent. That's how a hierarchy works. And a point of note here, that every child can have just one parent, but a parent can have multiple children, as you can see here. So coming back to the transforms, we can also echo the transform. Like right now we saw that there is some relationship, but we can see exactly what the relationship between two frames is by running this command, tf tf echo. And then if we say we want relationship between base link and the laser sensor link, press enter. So we have this relationship that it's translation of 0.435, that is like the height between the center here and this center, and rotation is almost is 0, so it's both of them are facing in the same direction. So we saw the relationship which was predefined. Now let's try defining our relationship by ourself, by our own. So the first exercise is about that. We have to define a static transform publisher for the Kinect here, the device you see here, and the base link. There is another transform publisher which we'll talk about later, which is called transform broadcaster. But for now, let's first see what is a static transform publisher. So first we create a package, let's say mm, static transform. So we created a static transform here, and let's make a launch file here. mm, New file, let's say launch transform dot launch, and let's open it. There is a format which we can copy from here to define a static transform publisher, and the type is XML. Actually, where is XML? Should be in the end. Yeah. So this is how we define a static transform publisher. We have the package transform which we are using. The type is static transform publisher. We can name the node as transforms, and here we have to define the x, y, z, that is the height information between the two. So at what height is the Kinect from the base, and what frames are we using will come here. The frame ID of the parent and its child frame ID, and what is the period between the two transforms that we want to generate. So how fast is the transform getting updated? Here you can see when we used it, it was updated every second. Actually it's milliseconds, so every millisecond it's getting updated. If we don't want it to get updated so fast, we can just increase the period in here. And we know the yaw pitch role also, that if there is an orientation difference, we can define it here. So for an assumption, we are defining x to be the same, x to be like let's say -2, y to be the same. So x is this direction, y is this direction, and z is this direction. So z is also some quantity. Since it's 0.435, so it should be little less than 0.435, let's say 0.2, and that means we have to define this also to be around 0.1 or something, minus 0.1. And your pitch roll will keep it like 0, since we are assuming they are facing in the same directions. Frame child we can keep as kinect. Let's see what are the frames here which we have. So there should be a kinect frame. Yeah, this one, pole kinect one link, or this is for the pole of that. We don't have a kinect frame here. So the camera RGB is actually what is a kinect. We don't have anything as kinect, do we? Let me check. So the kinect link is not defined. We have to define it. When we say kinect link, it will create a new frame, and the way which we do is, we don't want the kinect link to be the parent, but the base link should be the parent. So remember, we can just define one parent for any child and multiple children for one parent, and we'll just define the period in millisecond to be 1, and we are done. So we defined it to be around somewhat in behind at 0.1 distance and at a height of 0.2 from the base. And let's first launch this file. We have made it, so it's inside the package static transform. So let's say ROS launch static transform, then transforms.launch. So it's working now, and we can check the transform between the two by running the same command that we run earlier, that is transform echo. Now our parent frame is base link, and we have to check whether a kinect link is there or not. So yes, it's working. You can see this is exactly what we defined, and you can check again by stopping this transform publisher, static transform publisher, and running this command now, and you'll be thrown an error that there is no frame for that. So we don't have that anymore. Now I want to break you some news here, that the thing that we did here of defining a new frame and its relationship with old frames, which we call as parent frames, is actually not very much required in the real world scenario, since all these are defined in a URDF file, which we saw earlier also, what is a URDF file, and this is just to get the concept. It can be very helpful if you are adding a new sensor later after defining the URDF file. Maybe it's a temporary hand or an actuator or a Kinect which you decided later. So in that way you can be very helped by this static transform publisher, but the general approach is to do this transform publishing inside the URDF file, not in the launch files. So before we proceed, I just missed one topic, which was about the transform broadcaster. This is another kind of a relationship definer uh, for the transforms. So in here we use static transform publisher because the height of this Kinect and the position and orientation of this Kinect was always constant with respect to its parent frame, that is this base link. It's not changing with time, so that's why it's called static transform publisher. If we have something like a rotating laser which is uh, changing its orientation with respect to the base frame, or maybe a hand like this one which is changing its orientation and position also with respect to the base frame, then we need to use this package called as transform broadcaster to define that relationship as it changes with time. So that's for the transform broadcaster. You can see it in details on its website. Now what we are going to do is we are going to dive deep into SLAM Gmapping node. So first we'll get an overview about it by going to this website, Gmapping, and we have these things, these headings, which are the major things that we have to see. So in SLAM Gmapping node, it subscribes to these topics and it publishes these topics, and it uses these services and these parameters. So this is the main information which we need to understand. One is it subscribe to the transform and the scan topics. So it takes a scan and it takes the relationship between the odometry and the scan and the base link, as you remember what we just did. So that's why it subscribed to these two topics. It publishes these two topics, the map and the map metadata and the entropy, which is not very much connected right now, and it uses these services. So if you call this service, you can get the map as we did in earlier lectures. This is the main focus for this lecture. All the parameters that a user can change to generate a better map according to its own requirements. So there are so many parameters, and we are going to understand and execute few of them and leave others to its default values, since it's okay to make it work. So the first parameter that we are going to look into is the base frame, which is written here. So the default value for a base frame is base link, and that's why we have this link named as base link, as we saw earlier, because that's the default value that a Gmapping node can understand. And if we change that name, we have to change it here also in the parameter, and we'll see how it's done. And the map frame is by default taken as map, odom is odom, and the map update interval is 5 in seconds. So these three are okay, we shouldn't change those three, but we can change the map update interval right now and see if it improves the ability of slam gmapping node to generate a better map, a faster map. So first thing that we are going to do is first we are going to see um, sorry how it is working, what are the launch files that are already defined. So let's go to this package gmapping demo. So the package name is turtlebot navigation gazebo package. Let's see if we have it here. Yeah, we have. So let's see if there is a launch file which we can find, and inside here we will have gmapping demo.launch. So let's see, nano, or let's just copy this. So cp mapping, let's bring the working directory which we are using. So we have to copy it here. Yeah, this is the place where we are going to copy it. We should have it here now. So what will be the name? Gmapping demo.launch. So we have to change it a little bit. It's not in Catkin workspace, it's in the source of that. Now we have it here. So now we can see what it is doing. It is launching gmapping.launch.xml. So we have to see that file now. Let's copy it again. There will be a folder for turtlebot navigation and it will have a launch file. So let's go to that location now. So turtlebot navigation, then let's go there, launch files, gmapping. This is the next thing that we need to copy, gmapping.launch, and we'll put the same address that we were using. We'll get it here now. So this is the actual XML launch file that we needed, and we can use these values as it is working in our case and change some things, like make some tweaks to see if it affects the robots working. Let's make a clear screen right now. First let me just, and let's just go back to our working directory. Yeah, this one. So we have one launch file here, and the activity that we need to do is we have to make a package called as my mapping launcher and use these values there. So let's do that. Oops, sorry. Now it should be named my mapping launcher, and then we have to use these two files there, and let's see if we can make a folder here. a launch folder here, and let's make a include folder here. Just to make it look better, and it wants me to make a my gmapping.launch and gmapping.launch.xml with the same data that we copied from the original file. So let's do it. So let's make it my gmapping launch. So we have to copy this data into our launch file, the newly created launch file, and change the value to the one which we need to point to, which is the gmapping launch.xml, which we created here. So the name of the package got changed from Turtlebot navigation to my mapping launcher. The folder is not inside launch now, it's outside launch. It's not having this folder now. So now we have directed it to the new path gmapping.launch.xml, and it should work. Now let's just open gmapping launch.xml and copy the values from here and paste it here. The thing that we are going to see first is whether it works or not. So let's try launching it. Cross launch my mapping launcher. And let's say my mapping launch. So there was an error. Because it says my gmapping launcher not found. Let's see where. Oh, it's my gmapping launcher. It's my mapping launcher. That's wrong. Let's see again if it works. Yeah, it works now. So we have copied it successfully, but now we need to tweak it to see the changes. First, let's see what is the parameter value for one of them, which is like if we say ROS param get, let's say map update interval. So first we'll see what all parameters are available. So in SLAM gmapping we have so many parameters, and we were looking for map update interval. So we'll say what is the value here by asking for ROS param get and doing this. So sorry, it's not param get. Okay. So it's 5 right now. Let's change it to maybe 10 and see whether it changes. Let's run it again, and once it's running, let's get it now. Okay, it's 5, still 5 because we didn't save it. Now it's saved, so we have to do it again. Let's see if it gets changed. Yeah, it is working now. So we can tweak these values to make changes in the parameters, and the result will be reflected when you create an actual map. So what happens now is the map now updates every 10 seconds. So it will be slower in updates. We can see it by launching the Turtlebot navigation pack. We can see it by using the command Turtlebot navigation package, and let's run it. Arvis launcher to see the output, and let's open the Arvis window now. See, so we have a map now, and it's right now at this point. Let's see if we change it to like 100, it will not come as fast as we saw here. Let's see. Now let's just update it. So it's about laser scan, not map. Now right now it's not here. We have made it to be 100. Let's see how fast it comes now. It will not be here until 100 milliseconds, and it won't update until that. And if I make it to 1000, it will be even slower now. So I have took more time now. So that's how it affects. Let's go and to see if we can change other things and get a better map after that. So maximum range sends the maximum range that a laser can look at, and it should be slightly higher than the real sensor maximum range. So the maximum range here is 8. If we change it to maybe 2, let's see what happens. So it's the maximum range, and we don't see any difference until we have something at that maximum value. So if we change it to point, if we change it to 0, let's see what happens then. Oh yeah, so we have the map getting updated because of it. So we change it to 0.1 and the map is so small now. If we change it to this, let's see what happens now. Now the map size becomes little better or not. No, it's very small. So if we want to change the size, we have to make this value to be like 1. Let's see what happens in 1. One is also small, and let's see what happens with 10. Now we can see something, and that's what we wanted to know. What map should it update, how much map should it update after getting the laser scanning data. And when we change the maximum range, worked. Let's try changing maximum U range, which says it sets the maximum usable range of the laser. The laser beam will be cropped to this value. So let's change it to maybe 2. Let's see its effect now. So this is like the area which it covers in angles. So it's this way now. It reduced it. Let's just get back to the original values. It was like this. The minimum score is, it sets the minimum score to consider laser reading good. It's basically whether we should take each and every laser or remove some of them, filter some of them. So minimum score right now is around 200. Let's make it to 1 and see what happens. So when it was 200, not all of them was being taken, but now it is taking more. And let's change it to 1000 and see the difference. So it is getting filtered now. You see, it's more granular now because it's rejecting some areas now. So before starting, we have to we have to close this and change these parameters. Then only that we did. We can change the map dimensions also. So the total area that you see here is quite big right now. We are not mapping that area, so we can change the x min y min value here by changing this one. Let's say x minimum value will be about 0.1, 0.5. Let's make it half of what we are seeing. This was the original one, and when we launch this, it got reduced. Let's make it even smaller now, and let's say 0.2, 0.2, 0.2. So it's reducing now, and you can get as small as you want. And the delta is setting the resolution of the map here, so it's quite small and it understands even a very tiny bit of details. But if we make it like 20, let's see what happens. So you can see it's not able to map because it's very very low resolution. Let's make it back to a very small value, 0.001. What happens now? Again, at this delta, it's not able to work because it's quite small, so it's not able to do it. It's like too small. So let's see if it can be made back to the so see, the delta is so small that it's granulated now. it's taking each and every laser separately now. So that's how you can change the delta value to get the perfect fit for your application. And let me change it back to the original values before we go ahead. So the next thing that we can change is linear update, angular update, temporal update, and particles in here. And let's see, these are the current values here. So linear update means the distance that the robot has to move in order to process a laser reading. So if it moves at least zero point 0.5 units, it will update its scan. Only then it will update its scan. Angular update is if it rotates 0.436 units, then it will update its scan. Temporal update and resample threshold means that in between the two scans, how much it will wait. So we want it to be based on linear and angular update only, so we just switched off temporal update by putting it -1. And number of particles we define in the particles place, which is 80. So it is taking 80 laser scans to generate a map now. And the next thing is to understand how we can remap some topics. So we can change the topics by manually modifying it. And so after building the map here, we can also create a bag file to save the readings that we have to generate a map again in a simulation without running the robot. So first let's see how we can create a bag file, and before that we'll run this command in order to be able to move the robot around. So robot is Battlebot navigation, I think so. It should work. No. So the package that we are going to run is keyboard teleop.launch, and now we can move the robot around to generate the map. And you can see it here as it updates. Sorry, we close the RVS file window, so let's just run it again. There is an error. So now we can move the robot around and update the map based on that. And as we move the robot, we have a better map coming in the picture. As you can see, now what a bag file does is it records all the topics which was involved in making the map. So we have the laser scan, Kobuki laser scan, and Odom. We can record these topics by using the ROSBag record command, and as the laser moves, it gets stored. So as the robot moves, it gets stored. So let's just do it, and it's storing it. And I can move the robot around and all the values will get stored. Then it's storing the laser topic, and the TF topic, which is the relationship with laser, baselink, and ODOM. And using those topics, I have created a bag file, and we can use this bag file. When we stop it, it will get stored, not the this one but this one also. So it recorded the ROS bag record file here. So if we see here, there is a my laser data dot bag file. Let's cp that into the correct location. Mhm. So now we have my data laser bag here. Yeah, now we don't need to use the keyboard teleop anymore, and we also can stop other things which is not required, like the laser scanning driver of the turtle bot which we were using earlier, my gmapping.launch. We don't need it. We can just run this launch file, and we can change the, we do need slam gmapping though, so we'll run it again, and we can just play the back file. And using this command, ROS bag play, and we should be in the correct directory. So ROS bag play, we have my laser data. So right now we have something like this. Let's first close it so that we get a fresh beginning here. So right now we have the robot to be like this, and let's run it. My laser bag, let's see it in action. Oh, we have to define which. So that's all for today. We have seen how we can do mapping using laser scan data and odometry, and we did some changes in the configuration files and saw the results in our RVIS window, how it can improve or even make it worse by changing those things, parameters. And also bear in mind that once you create a map, we don't need to use SlamG mapping anymore. So if we can master this topic, we won't need it later in the other areas when we are doing the navigation. So if you have the correct values here and you have defined proper transform and you are able to get a perfect map, that's just one time and you are done. Then you don't need to worry about the same thing in future. So it's very important that you perfect it right now so that in future you don't have any problems with it. See you next time.